today we are going to hopefully start quantizing our scalar field. And we're going to try to develop the quantum theory as far as we can before we move on to QED itself, quantum electrodynamics itself. The reason is that we need to set up perturbation theory to calculate what are called correlation functions, and it's most easy to see it using scalar field theory. And then once we get used to it, then we will see how to generalize it to QED itself. And then finally, I hope by the end of the semester we'll at least calculate a couple of basic scattering processes, just so that, especially for those of you who are doing high energy physics, you have some tools to help you calculate basic processes in your research. Although I don't think in this semester, I don't think we have many. I think there's one high energy. It's not here yet, but it's high energy experimentalism. Okay, so yes, that's our friend. I think you're the only high energy experimentalist here. Is that right?
Yeah.
I don't think there's any. Yeah.
There's not a guy here.
Hmm? Oh, there's another guy? Oh, okay. Okay, anyway, yeah, okay, so, we were talking about how, for the free scalar, let me just do it and then hopefully my Dropbox is going to boot up. We're talking about how the free scalar field is in fact nothing but a bunch of harmonic oscillators. And there are at least two ways I know how to look at that. One way is to look at it in position space, and if you discretize it, the derivatives will act as basically couplings between neighboring lattice points in space. Meaning the harmonic oscillators are basically the field value at each point in space, and the derivatives will couple the field values at one point with the field values at neighboring points, because that's what the derivative is. They're basically the Laplacian in particular, as you may know, is the average of the neighboring points, right? So this is something that you may have learned, especially if you take a numerical analysis course. You learn that the Laplacian is, in fact, the average of the neighbors. But in our case, by taking the continuum limit, you find that basically field theory in position space is the continuum limit of an infinitely coupled harmonic oscillator system. Especially if you have an infinite space, that's basically what it is. If you have a finite space, then you can truncate your Fourier, you can truncate it but still there'll be an infinite number of points. The other way is to in fact go to Fourier space, and then the whole system completely diagonalizes. So in fact, that's exactly what Fourier analysis is about. In position space, while points are coupled to their neighboring points because of the derivatives, by switching over to Fourier space, you're basically diagonalizing your system, the kinetic, the wave operator of your of your scalar field theory. And there you can see very clearly the normal modes, right? So when you diagonalize, I hope all of you have, in a classical mechanics course, solved the system of coupled harmonic oscillators. And once you diagonalize the system, then what you're going to find are called the normal modes of the system. They'll oscillate in different directions and have their own characteristic frequency, right? That's what the normal modes mean. So the Fourier transform, when it comes to the scalar field, is in fact basically diagonalizing the system so that each Fourier mode is nothing but the normal mode of the system. Right? So let me just write it down. As much as possible, when things are very general, I'm going to use little d is my number of space-time dimensions. Sometimes I'll use capital D, but capital D can be a little bit confusing because our covariant derivative is capital D, and later on our path integral measure is also capital D. So sometimes I'll use it, but I'll probably stick to little d. So this part is not unfamiliar. We've already solved this before. And in fact, let me just remind is 1 over square root of 2k0, which is energy. Energy is a function of k of alpha e to the minus I k mu dot x. Okay, so this is a 4 plus complex conjugate. And what I'm trying to say is that so k is square root of k squared plus m squared. And what I want to say is that the Fourier modes are the normal modes of the scalar field. And this is true even in the classical case, right? But now we're going to quantize it, and we're going to give it additional meaning, which is that not only are they the Fourier modes, these are also the particles. They correspond to the wave function, essentially. It's a little bit, that concept is a little bit fuzzy in quantum field theory because, as you'll see, we will create particles, and I'll show you how to construct the most general one particle state. But yeah, sometimes books try to avoid talking about the connection to the non-relativistic case. So I'll only just sketch what happens. But roughly speaking, these are basically the wave functions of the one particle states of a particular momentum k. And so not only are the plane waves, these Fourier modes, the normal modes, they are also corresponding to excitations from the vacuum, which then we interpret as particles. So this is classical. Okay, and the quantum. In the quantum case, what we'll have is that we have excitations of the vacuum. What I mean is the following. This Fourier modes, in the classical case, correspond to Fourier modes. And in the quantum case, they correspond to excitation to the vacuum, wave functions of the one particle states with momentum k mu. Okay, that's what it means. So that's why you often hear this statement that particles. What are particles? Particles are excitations of the quantum vacuum, and we will see how it comes out with this formalism. But I also want to remind you guys that conceptually we're taking two paths, right? One path which we spend considerable time in the beginning of the semester is to understand symmetry for its own sake, right? So we start with usually the basic definition, Lorentz boosts, rotations, and so on, and we try to abstract it so that we can construct representation theory around the more abstract version of the group. And from there we discovered what the combination of that was that, although we didn't fill in all the details, but the combination of that was that we discovered that on a Hilbert space, if you have a Hilbert space, that you can realize these Lorentz, that's actually the main point. The Lorentz space-time and Poincare space-time symmetries, we discovered that the eigenstates of these generators, the simultaneous eigenstates of these generators that are important for observables, are labeled by mass and spin. And so even though we didn't know where it came from, we knew from the symmetry arguments that these guys are going to be labeled by mass and spin. So at the time I told you this is going to be, the Klein-Gordon equation is eventually going to lead us to the spin zero massive and massless particles, right? So then later on we took a different path, which is to start from the field's point of view. And there we are also guided by symmetry, because we want our solutions and our equations of motions to be covariant, meaning take the same form in all inertial reference frames, right? And this is to ensure that our physics is frame independent. And so what we're going to do is we're going to start to quantize those relativistic field theories that we've looked at, right? We've looked at Maxwell, we've looked at the Dirac equation coupled to the vector potential, and also the scalar field itself. And now we're going to quantize it, and then we see how these two things are going to come together, right? Upon quantization, we'll see that the particles that we kind of could see should come out of symmetry arguments, in fact, are going to be generated by these guys, right? So it will take a bit of time, but we will see it for scalars pretty soon, right? The Dirac and the photon is going to take a bit of time, but let's do it with the scalars. Okay, so let's do it. So in fact, what we do is we're going to appeal to our knowledge of the quantum mechanical commutation relation. Right? So this x comma p is I. Well, there's a h bar, but as you know, we're setting h bar to 1. Now, for what we're doing here, we're doing a field theory. So we start with a Lagrangian, that we know is basically 1/2, and then the kinetic term minus the potential term, which in this case is just the mass term. So what we do is now we split this up into the time derivative term, phi dot squared, minus 1/2 gradient of phi dotted into itself, minus m squared over 2 phi squared. So why we write it out this way is because now we can, just like in Hamiltonian mechanics, we can define the conjugate momentum. So in classical mechanics, we have a Q and we have a P. Okay, P is the conjugate momentum to the classical position variable Q, where Q doesn't have necessarily to do with the position in Cartesian coordinates. Right? It can be angular coordinates, can be anything really. But for each sort of position, there is a conjugate momentum. And so how do you calculate that? This is always defined to be the derivative of the Lagrangian with respect to the time derivative of your Q. So what we'll discover is that, in fact, in the classical mechanical Q and P will find the analog in the quantum field theory. In this case, we're doing scalar fields. Will be phi is the Q, and pi will be dl d phi dot, and we'll soon see that this is actually just phi dot itself. Okay, so this is in fact now going to be phi dot, because it's just phi dot squared, and this will be phi dot. Now, of course, this is because the field theory is simple, right? You can imagine that you can cook up more complicated Lagrangians, then pi, the conjugate momentum, may no longer be just the time derivative, right? There are these, the most general scalar field theory that has two derivatives are called, there's this class of theories called Quantization theories, and there, the conjugate momentum will be very complicated. Anyway, so now that we have the pi, we can construct, in fact, the Hamiltonian. So for example, H, phi dot now you know is in fact pi, so it will be actually pi squared, and then, almost wrote down the full answer right away, but let me just say, is pi q dot, and then minus Lagrangian, but now the Lagrangian you want to express in terms of phi and pi. Okay, so how do we do that? This is now pi, so this is pi squared, and then minus Lagrangian is now 1/2 pi squared, and then minus 1/2 gradient of phi squared minus m squared over 2 phi squared. So in fact, it's just a sum of the kinetic energy, half pi squared. This is, if you think about this is something like p squared over 2m, right? It's not really the same, but the analogy is, it helps you to remember, this is p squared over 2m, and then this is 1/2 rad phi squared plus m squared over 2 phi squared. Okay? And that's the Hamiltonian. So what we're going to do to impose this guy, the analog of this guy, is to say that phi, as a function of time and space, when you commute it with pi of the same time but different points in space, potentially different points in space, this is the subtlety about working with infinite degrees of freedom, right? Every point in space, remember, is a harmonic oscillator, coupled harmonic oscillator. So in position space, what you will say is that at this event, my Q is going to have a commutation relation similar to in quantum mechanics with the its conjugate momentum at possible the same time but possibly different spatial point. If it's at a different spatial point, in fact, we just want it to commute, okay? Because they are not the same, because this would not correspond to the conjugate momentum of this, because it's a different position. But if they're the same location, then you want it to obey x comma p equals to I. And that tells you, in fact, this tells that this should be equals to I times a delta function in space, x minus x prime. Right, so again, when x is not equal to x prime, they commute, because they're not the same. This is not the conjugate momentum of that, if they're not the same point. But if they are, then you want it to be 1. Right? But this is now a continuous degree of freedom, continuous and infinite degrees of freedom object. So you represent that 1 through a delta function. Okay. And now we have to remember, these are now operators. Phi and pi are now operators. Which means that what we are, so the big departure from what we've been doing so far is that when we first wrote these guys down and we say that, oh, we want them to be covariant and so on, and that's all great. But those were classical fields at the time that we were trying to look at them. And of course, there is some historical reason for why we do what we do, right? Because of the photon. This is something I mentioned at the very, very beginning of class after this semester, which is that why we do quantum field theory was triggered by the fact that the photon was known to be a field before we quantized it. The electron's wave function was then discovered through quantum mechanics. So this is why we deal with fields. But now we realize that to really describe particles, we need to promote these guys to operators. So now this guy is an operator. And this guy is an operator. So one of these objects must be operators. But these are just classical plane waves. These modes, I just said they're wave functions, right? E to the minus ik dot x, these are just functions. So the only thing you are left with to quantize, to promote into an operator are actually the coefficients. So this is an operator. Okay, but so I'll leave this on the board, but we'll build this up slowly and see how exactly these guys are operators. We'll find that they depend on momentum, so maybe I should write it down here. They depend on momentum, and they will obey their own commutation relations. So, but before we do that, I want to show you that since they're now operators, you got to be a little bit careful here, which is that now we are basically working in the Heisenberg picture. So we're now in the Heisenberg picture. The reason why you can tell we are in the Heisenberg picture is because our operators now depend on both space and time. And the reason why I want to just jump straight into that, so Peskin and Schroeder has a different approach, right? So at first they do it in just Schrodinger picture, just x, and then they do a time evolution, they do a unitary transformation, and then they promote it into the Heisenberg picture. But I think it's just, because symmetry is important, I think it's just much more straightforward to just begin in Heisenberg picture, because we know that our field theory should be relativistic. And if you have a relativistic field theory, it's conceptually much easier to recognize that these guys have better beam. um, both space and time dependent. Okay? So what we'll see, I should also write down, so this is the x comma p, so x, phi should, at x should commute with phi at x time. So if I don't put an arrow, it means that it's a space-time location. So let me just write it down. So this is between phi and pi, and then between pi and pi, they also commute. Okay, this should be familiar from quantum mechanics, but for us, this is going to be a postulate. Okay, it's from this point of view, it's a postulate. We impose these commutation relations on our fields and see what they give us. Now, what we're going to do is we're going to also derive this equation, because this is from the classical field theory point of view that led us to that. But now that these are operators, we need to impose the Heisenberg equations of motion. Okay, what are those guys? Well, Heisenberg, so you might remember that the Heisenberg equations of motion tells you that Q dot is in fact I times the commutator of the Hamiltonian with whatever variable that you have. Right? So there's a classical mechanics analog of this equation as well, where the time derivative of your classical variable is the Poisson bracket between the Hamiltonian and whatever variable that is. Right? So that's why even in classical mechanics, H is the generator of time evolution. And now we have come to the quantum field theory analog of that. And so if you're not familiar with this equation, look up your quantum mechanics text, right? And remind yourself of that. The main difference here is that we are going to deal with fields instead of just one-dimensional variables. In fact, what we're dealing with here, when we call it Lagrangians and Hamiltonians, I'm being a little bit sloppy here. This is actually the Hamiltonian density, so I should write it with a script font. The Hamiltonian itself, which is H, is actually the integral over all space of this guy, 1/2 pi squared plus 1/2 grad phi squared plus m squared over 2 pi squared. Okay? So this is basically the sum of all of the harmonic oscillators at a given time, and that's what the Hamiltonian actually is. And now we're going to compute what is phi dot. What is phi dot? Better change the marker. So what is phi dot of is I, and then now I have to integrate with respect to x, okay? And let me actually use a different variable. Maybe I'll call it x prime. So I'll integrate with respect to x prime, and my phi dot is with respect to t and x, right? And so this will commute. This would, what I'm doing is I'm computing the commutator of 1/2 pi squared plus 1/2 grad phi squared plus m squared over 2 phi squared, all with respect to x prime. I'm trying to commute it with phi. Okay, phi of t x, because I'm trying to find its time derivative. So I must take this operator and commute it with the Hamiltonian.
phi and pi as operators.
That's right.
So what we actually do is integrate over the eigenvalue of operator.
We're integrating over all the harmonic oscillators for a given time. Not quite eigenvalue. I'm not sure where that.
Because we integral the operator.
Yeah, but that's because remember that we have an infinite number of harmonic oscillators, right? Infinite number of operators at y, because at each point in space and time, we have an operator. So what we do is we focus our attention on a given time slice, and we try to, the total Hamiltonian of the system is given by summing over all the operators at a given time, which means basically an integral over space. Yeah. So the main thing that is not very coherent about this formalism is that you have to pick a time, and then you have to integrate over space, right? And so you can argue that it's doesn't look very coherent, and the justification of this is ultimately that you do, despite looking non-coherent, the end result, just starting from something that doesn't look coherent, the end result is coherent, right? The Heisenberg equations of motion for the scalar field is in fact coherent. Okay? So, in fact, because this is true, because this is still true, immediately we can come to here, right? So that's why I wrote this on the board right away. Except the only thing I need to change is that it's no longer this complex conjugate anymore. I should call this permission conjugate, because these are now, this guy is now an operator, and I need to not just take the complex conjugate, but take the permission adjoint. Okay, and so now let's look in Fourier space and see what's the analog of this guy in Fourier space. And this is where we're going to discover the why I keep saying that these are harmonic oscillators. Okay. Okay. I think I can erase all of this. So this calculation, I believe you can find in Pascal and Schroeder, but I think they take too long to get to the space-time picture, right? But since I'm emphasizing the space-time symmetries very much, I claim that one should in fact start from the Heisenberg picture right away. I also should mention, I forgot whether it's going to be a homework problem, but there is actually a more coherent way to quantize your scalar field, but I will try to remember to say this after we do the Fourier space, because that one takes a bit of discussion. You have to know something about the Green's functions. Yeah, but for some reason that way of quantizing is not very popular. Let's see. I don't think we need this. Yeah, I don't think we need this, but I will leave the position space commutation relation on the board, because I want to compare between this guy and the Fourier space. So in fact, let me write down the full guy. Right, so it's alpha. I think Pascal and Schroeder calls it A. So what do I call it in my notes? A or alpha? A. Okay, maybe I should stick to A then. A. A dagger e to the I k dot x. Okay, remember this is a not four, it's rather D Lorentz product, not a spatial dot product. Now, what I want to remind you guys is the following. We know that this is true, and in fact, what you see over here is that if you only went to Fourier space, but not Fourier space-time, then what you will discover is that in Fourier space, I think I've said this before already, but let me just say it again. This looks like the equations of motion for the harmonic oscillator. Okay. And in the quantum mechanics case, in fact, you can also work in the Heisenberg picture for the position operator. And you will find that the harmonic oscillator would in fact obey exactly the same equation. And then, let me just remind you, you can find the solution in terms of these ladder operators. Okay, X, this is now quantum mechanics. Okay, so this is now quantum mechanics. So let me draw a line over here. And what is this Heisenberg solution? It's in fact 1 over square root of 2 omega. This is actually why I keep writing my solution with a two energy here. What you notice is that E corresponds to the frequency, angular frequency of your harmonic oscillator. This is why when you first start learning quantum mechanics, without even telling you where it comes from, you're just being told that angular frequency is energy, right? H bar times omega is energy. So at the fundamental level, it comes from the fact that there's a dispersion relation, and the energy is in fact angular frequency. Anyway, so the Heisenberg picture solution for your position operator is 1 over square root 2 energy, and then you have A dagger, and then e to the I omega t. If you like, you can minus t naught, and then plus A times e to the minus I omega t minus t naught, where t naught is the time where the Schrödinger and the Heisenberg picture coincide. Okay. And what are these A and A daggers? So A and A daggers are built out of the Schrödinger picture operators. So A is in fact given by I over square root of 2 omega, and then P momentum operator minus I omega x. And so A dagger is in fact I over square root 2 omega P plus I omega x. Okay. So in fact, it is this guy that tells you these relations that are a direct analog to the harmonic oscillator problem. So in fact, what I can do over here to make it look more like a harmonic oscillator is to erase, is to do the following. So this guy, k dot x, is energy times time plus I k dot x. So I can write that down over here. And then this guy is I k0t, so it's E times t, and then again times the plane wave. Okay, so what we discovered is that the main difference between this and this is that the A's here are just corresponding to one degree of freedom, x, the position operator. But now, our position operator, the analog of the position operator, is phi of k, but k is a continuous label. K can run over all possible momenta. So, in fact, the main difference between quantum field theory, free quantum field theory, and the harmonic oscillator is that instead of one degree of freedom, you now have a continuous label. So I sort of have to come over here and stick in a k over here, and so omega will depend on k, a will depend on k, and so on, right? And that's exactly what's going on. What is most important is that just as these guys obey a commutation relation where a dagger is 1. So my claim here is that over here we'll discover the same thing. A of k commuted with a k prime dagger will be equal to delta function of k. Okay. Actually, I've got to be a little bit careful with my sign of the k. So let me just stick it back in. Okay, this is actually e to the I k dot x, and then this is minus I k dot x. Okay, but we'll stick to this convention. But you should think that you should keep in mind that basically up to a sign, each plane wave mode, the coefficient of each plane wave mode has an A and an A dagger, just like the harmonic oscillator has an A and A dagger mode. Okay, that's what you should keep in mind.
Does A and A dagger affect exponential IKS?
What do you mean?
Because a creation and
You mean whether it acts on it?
yeah.
Yeah, no. It's just an operator, but these are just functions, very classical functions, just complex functions. Yeah. What they act on, I will get to it very, very soon. Yeah, certainly by the end of today, I will get to that, and you'll see where particles come from. But let me just go on for a little bit, and then we'll take a break. So, so what I do want to do is to, in fact, show you that this guy is consistent with that guy. Okay, so let's do that. Okay, so let's in fact calculate this commutation relation, but pretending that I don't know this. Okay, let's pretend that I don't know this, but I will impose this instead, and then I will be able to recover that, so that you can see that they are consistent with each other. Okay, so what is that? That is phi of x and pi of x prime. I should be careful, right? So this is t x, and this is t x prime. I want to find the commutation relation. And pi, remember, is phi dot. Okay, so now I have two integrals over momentum. So the first one I'll call k. The second one I'll call k prime. So again, I have many integrals to write. So every time I have a measure like that, I will just denote it as k and k prime. And so I will have a 1 over square root of 2ek, and then 1 over square root of 2ek prime. That's why I need to write the momentum, because otherwise it would just look like EE, and I'll think it's the same thing. And then now I have to commute them. So I will have the commutation of a k e to the minus I k dot x plus Hermitian conjugate. I'm going to erase it. Anyway, we'll see it again very soon. And then this is going to be commuted with ak prime. Let's write it out. Commuted with ak prime e to the minus ik prime dot x prime plus ak prime dagger e to the ik prime dot x prime. Okay? So, I should say, so A, just like in this case, A commutes with itself, and immediately from this you can deduce that A dagger will also commute with itself. So it's only A and A dagger that has a non-trivial commutation relation. So therefore, when you work this out, actually it's not too complicated. A will commute with itself. A will not commute with A dagger. A dagger will not commute with this guy, but it will commute with this guy. So there are only two terms actually to worry about. So the first term, let's write it out. K prime, 1 over square root of 2ek, square root of 2ek prime. And then now A will needs to be commuted with A dagger. This is e to the minus ik dot x, and then plus ik prime dot x prime. And then A dagger A, so let me write it as minus AK prime commuted with A dagger K, and then it will be e to the ik dot x minus ik prime dot x prime. Okay? Oh, I'm sorry, there's a dot here, right? I'm thinking I made a mistake. This one has to be, so I need a dot here, so let me, if I take a dot of this, I get minus IE k prime, a k prime, e to the minus ik dot x. And then if I take a dot of this guy, I get plus IE k prime, a k prime dagger, e to the plus ik prime dot x prime. Sorry, these are all primes. Okay, so the main thing that I missed out was that when I commuted this guy and that guy, I need to stick in a IE k prime. Okay. Again, this guy and that guy, I need to multiply by e to the IEK prime. And then this guy and this guy, I swap the A dagger and A in the combination relation, so I have a minus I, but now I have a minus IE, so I have plus IEK prime. Okay, so that means that I can just pull the whole thing out and put it here. IEK prime. Okay? Now, this guy, if I impose this, will collapse the two delta functions, the two integrals. Right? So it's very simple. I commute and I get a delta function, and all the k's primes will become k's, and I just have one integral. So I get I. But now, you see, I get e, and then the square roots become no more, and I just get e. So I get 2 ek, and of course they cancel. And then I get, now this is 1, because it's delta function, and I took out the delta function. And this is what? This is minus I. Now all the k's are the same, so it would just be ik dot x minus x prime, okay, plus e to the ik dot x minus x prime. But remember, x is t x vector, x prime is t x prime. Okay, because we are working with the equal time commutation relation, but the spatial positions are different. Okay, so when we work this out, this is actually e to the t minus t is 0, so I really have ik vector dot x vector prime. This guy is e times t minus t, so that's 0. So this is actually minus ik vector dot x minus x prime vector. Okay? And therefore, when you since there's no more e over here, when you integrate over k, that's just the delta function. And there are just 2 of them. It's the same thing. Doesn't matter whether it's plus or minus. So that would in fact cancel the 2, and you get I delta function of x minus x prime. Okay? So I claim you can go backwards, right? So you can go from the position space version and argue that this has to be the case. But here I'm just showing you the consistency of it, right? That you can just see that if you do impose that guide, then you will be able to see that the position space x comma p equals to I commutation relation, which in the field theory context is just phi pi equals to I delta function, is basically just 2 versions of the same commutation relation. One in Fourier space, one in position space. But the Fourier space one is the one that will allow us to easily see the particle interpretation. Okay, so we're going to take a break first, but let me just write this down. AK dagger equals to delta function is important for particle interpretation. Okay. Any questions at this point? No? Okay, let's take a 10-minute break, and then we'll come back to see, we'll come back to see this. Where does this indistinguishability come from? It comes from the fact that all these excitations come from the same field, phi. It's not from phi 1 or phi 2, phi 3. It's the same field phi from which we build up the raising operator. Without the field, there wouldn't be a raising operator to talk about. So all these momentum states, the n particle momentum states, all correspond to excitations of the same field, right? So physically speaking, there are all, these are n excitations of the same field. So it doesn't matter whether the electron going, building up the aluminum here, or the electrons flowing through, Donald Trump's phone, right? These are all electrons of the same field, the same excitations, the excitations of the same field, even though Donald Trump is living in the US and we are here, the electrons here are not in the same place. The fundamental field underlying the excitations, that what we call particles, are fundamentally the same thing. It is the same field permeating throughout the entire universe that's giving you the same electron. That's why the electron in his phone is indistinguishable from the electrons in this piece of aluminum, for example. Right. So that's something very important to remember. Something very fundamental to our description of physics, right? That it's really that just that field, that many fundamental fields in our universe corresponding to the different particle species, but all the particles of the same type are really just excitations of the same field, precisely the same field, because that field permeates throughout all of space and time.
Is capital N here a function of position?
No, it's just an operator that you get by summing the quantum mechanical number operator for each momentum, right? So if you don't sum over k, A dagger A is just nothing but a quantum mechanical number operator, but for each momentum. So the quantum field theory case would just be that I have got to sum that over all the case to get the total number operator. Yeah, so it doesn't depend on position because it's a number operator.
So it means we choose different mass, and then we can generate different phi.
If you have a different mass in your operator and your field theory, that would be a different field altogether, right? So in fact, so in fact, that's what I want to say. That's the next thing I want to say, which is that I want to remind you guys that these states are also exactly the quantum eigenstates of the representation, the symmetry operators that we will talk about, the momentum and spin operators that we were talking about much earlier. Right? So if you have a different mass, that will be correspond to a different type of particle. Okay, let me say that and let me write it down in verse. Right? So much earlier, we showed from symmetry considerations. We expected from thinking about Lorentz and Poincare symmetry that there will be these states with momentum and mass m and spin. Right? That's what we expected from just from symmetry arguments. Okay. Now what we discover is that what we're discovering here is the first realization of such a thing. So what is it? So A, in fact, square root of 2me, 2ek, ak dagger, acting on a vacuum, is exactly this thing. This guy is what? This is momentum k. Spin equals to 0 because it's a scalar. There's no other degree of freedom, right? So the spin equals to 0, and mass m. Okay. So if you have a different mass, you will call that a different eigenstate. which is not the same as this eigenstate, right? So this is not the same as k n prime s. So, but in fact, how do you construct something like that? You will have to cook up a different field theory where the mass is a different mass here. Okay, and so this is exactly what we mean by particles. You have to start with some definition of what your field theory is. Its excitations would carry the labels that come with your definition. In this case, you will have zero spin and mass m. And when you go to Fourier space and you add so this vacuum state is common to all the quantum field theories. Right? We have one universe, there's one vacuum state. But if you add the vacuum, on the vacuum you add A with the A dagger that comes from this quantum field theory, then it will create a particle that corresponds to this guy. Okay, so if you have another one, if you have another partial squared plus n prime squared, say 5, okay, then this guy from 5, dagger k, will create a particle of momentum k, spin 0, and mass m prime. Okay, but this will be considered a different particle from that. And moreover, this is in fact also the place where I want to explain why I write the square root 2k. It turns out that this is a little bit tricky to remember, because depending on your commutation relations that you impose, so I impose the commutation relation with this normalization because I want to appeal to the harmonic oscillator. But of course I can multiply throughout by some k-dependent factor, right? So f a k, f star, a k dagger, and then this will just be f star on the right-hand side times the delta function. So the normalization is not fixed by, there's no unique normalization. But once I fix this, because of the harmonic oscillator interpretation, I will need to insert this to produce a relativistic covariant. This is relativistically covariant. Okay, and what do I mean by that? Remember when we were talking about Lorentz and Poincare transformations, we said that there must be an operator of this form that we can implement Lorentz transformations on these states that we were able to deduce from symmetry alone. Right? So d lambda acting on k, in this case is just mass. Mass is an invariant, but k will be boosted. Right? So if this is ki, this will be lambda ki n. Okay, there will be some operator that I can implement my Lorentz transformations on the k. And this is